So this talk is about PetriNICs, specifically using them to model cyber attacks. Modeling cyber attacks from the KPEC database, excuse me, the KPEC attack. Okay, so in academic papers, one of the very first things that you have to do is defend why you did the research that you did, and so we always talk about, we say, okay, cybersecurity, is a necessary thing. It's getting more and more important. Research into it is very important. Basically, what is a Petri net? So Petri nets were formalized in 1962 by Carl Petri. He originally defined them to describe chemical processes. So I'm going to use terminology here, places and transitions. What he was describing was states and transitions, and when he said the word state, what he was talking about was a particular amount of some substance. But they've been expanded to describe various states in the broader sense. So, for example, one of the things that we use to describe, or that we use to describe Petri nets are, if I'm describing the assembly of a cabinet, then I need a piece of wood and I need a piece of metal for the cabinet, and so then I perform a process or perform a transition on those two things, and then I get an output for that. So that's basically what that's describing. Transitions cannot fire unless all of the places that are further upstream to them and connected to them via input arcs are also marked. So you see the circles here in this chart. This transition cannot fire unless both of the places that are pointing to it also have markings. So this is kind of terminology here. So you have places, you have transitions, you have two different types of arcs. So you have arcs that start in a place and end in a transition, and you have arcs that start in a transition and end in a place. Those are the only two types of arcs that there can be. So there aren't place-to-place arcs or anything like that. Now, you could have a transition that had an arc that fed back to the one of the places that originally was marking for it. So if something else marked this, like if some other transition further back to P1 was mediating whether or not P1 had a marking. So initially, only P2 had a marking, and then P1 didn't have a marking. Then theoretically, if this transition had a marking going back, when this did get a marking, if this when this transition fires, it would feed back, and so P1 would always have a marking, effectively. So that's a thing that you see sometimes too. They also have arcs that they basically call them inhibitor arcs. So basically, if a place is marked, then that transition, then it can point back to a transition, and then that transition is disabled. So even if the markings, or even if the places that are sources for it could cause it to activate, the inhibitor arc will prevent it from activating. So this is a formal method of describing processes for just describing anything. So these are different types of nets that you might see. Places can also be marked more than once. So you see in this example down here, this place has 2 markings. So what that means is this transition is enabled. A transition, as I said before, a transition cannot fire unless both of its source places are marked. So this transition is enabled because this transition right here does not have it's one of its places is not, or source places is not marked. It is not enabled. In this state, it cannot fire. When this transition fires, it's going to put a marking in both of the places that it has output arcs. So that's another thing to keep in mind. So for example, this cross A transition here, when this place gets marked, if this place is also marked, either one of these, I guess I should go back. Transitions can be stochastic. So basically, if there are 2 transitions that are enabled, then what we do is we pull a random number and we compare it to a firing rate that each transition has. And so basically, so then you can introduce some randomness into what happens in the process. So in this example here, this sequence example, both of these places are marked, so both of these transitions are enabled. So either one of them could fire, and depending on the rate of this versus the rate of this, if the rate of this transit to crossing transition is set to 2, and the transit to crossing for this one is set to 1, then at a random base rate, this one will fire twice as often as this one, but you don't know. It's just a matter of you run Monte Carlos and that comes out. So, but you can control the rates of transitions. So, let's see. This cross A versus cross B, these are interesting in that only one of these transitions can fire at a time, and when it fires, it'll feed back into this crossing open transition or place. So yeah, I think this is some kind of warehouse example. So this is the mathematical formal specification for a standard Petri net. Basically, what this is saying is in order for something to be a Petri net, it has to have places, it has to have transitions, it has to have arcs that go from both the place to the transition and the transition to the place. It has to have an upper bound on the tokens. So basically, you can put a limit on the number of tokens that any particular place can have. You don't have to, it can be infinite. Then there's always going to be an initial marking based, saying, like, because transitions, like, in order to start a net, in order to model the process, you have to have an initial marking talking about how the, like, basically a starting point. This basically says, hey, don't forget the starting point. Excuse me. And then there's a, so they also talk about the possibility of you know, there's a super space of any possible like configurations of this net. So because you can add markings to a net through transitions, so basically a transition can theoretically have one input and then many outputs. So theoretically you can be adding more markings into the net just by the way the net is operating. Or you can also, you know, have it shrink down to just one marking or just one token. And so the set of all possible you know, configurations of the net is this this B and P together. So that's just kind of how Petri nets work in general. I'm doing pretty good on time. So now you know, now that we have this idea of what, you know, how Petri nets work, in 2011 there was a paper that was written by Zakruska, and I cannot remember her name for life. She basically came up with an extension of the PetriNet formalism, where she added players and strategies. So basically, she's able to basically build Petri nets where there are these agents within the net that have strategies where they and goals where they're wanting to achieve certain markings, and the way they can achieve these markings is they have control over certain transitions, over the rates of certain transitions. So you have these it can be a person or a program, but it's basically some agent within the simulation that is changing the rates of the way of things that happen in order to cause markings to fire and thus get events to flow in the direction that they want. So what my team did was they took this paper and then added the concept of cost to it. So basically, what we do is we say, okay, that's a good way to model it. Now what we want to do is we want to say there is some cost associated with making this change, this rate change, and there's also a cost for if a transition fires. So, you know, in the example of cybersecurity, there is a cost of, say, adding a firewall to a system. That would change the likelihood that you're going to be you know, subject to certain types of attack techniques. Then, if you don't add a firewall, then the event that you might be subject to an attack, and it might be successful, might be higher. And so the transition that, like, if the, hey, this attack occurred and was successful, if that transition fires, then what we do is we assign a cost to you, basically saying, hey, you didn't make the investment, and so now you're going to be punished for it. And so it's basically a way of modeling, cost benefit, for lack of a better term. You can do trade studies using this technique. So this is the formal specification for Petri nets with players, strategies, and costs. So you have these original functions, but then you also have a set of players. So you basically can have an attacker, a defender, an observer. There's any number of defenders that you can add to a net. Then we specify a set of transitions that each player can control. So they have control over the rate of that transition. So basically this is modeling, yes, I spent the extra money on the nicer service. I'm backing up my databases on to a colo site or something like that, or to a cold storage. Some like different types of mitigation strategies that a defender might take, or doing extra research that an attacker might do, that sort of thing. Is so basically, in order to describe agents, and here I'm using the machine learning definition. It's basically something that can observe the world and has goals and has actions that it can perform in order to achieve those goals. So O is basically how it observes the world. We don't give every agent perfect vision into the state of the net, because nobody's omniscient in this system. So what we do is we specify different places, and when a place gets marked, the agent knows about it. So what we do is we say transitions can only be controlled by one agent, and that basically is so that you're being more honest. An attacker is not going to be able to have any control over whether or not I buy a firewall, but likewise I'm not going to have any control over whether an attacker goes through my garbage. I might be able to do some other mitigation for that, but that's just kind of like there are different ways of deciding whether, or of modeling whether, like, what happens in an attack. Different players might be able to see outcomes of attacks. So an attacker and a defender might be able to see, hey, this attack failed. The attacker might be able to see that the attack succeeded, and that might not be observable by the defender. But if the attack gets detected, then the defender might see that the attack was detected, and the attacker might not see that the attack was detected. So that's another way of modeling that. We also have the set of firing rates. We have the different maximum rates for each of the controlled transitions. We have let's see, what is delta? Or gamma? Gamma. Oh, so this is where we were actually storing the strategies. We record strategies for Petri nets in the actual rates as a mathematical function, and then it's up to the simulator, the person who's writing the simulation to decide how they're actually going to model the player. So you could have somebody who decides to write a full-blown reinforcement learning algorithm where they're going in and playing with different levels of Q and stuff like that. Or you could have somebody who's just like, no, the way it is good. I'm just going to run in a default random firing weights, and I just want to see generally how things work. Then you also have the two costs. So C is how much it costs to make a change to each transition that is controlled by players, and then D is the cost of a transition firing for each of the players. So the way KPEC models attacks, there are usually three phases. There's an explore phase, there's an exploit phase, and then there's a goals phase, where basically the attacker is learning information about the system. If they get if they get into the system, then you move into the exploit phase. Then they try and get the thing that they want, and then you move into the goals phase, where you understand where you decide whether or not they were successful and how successful they were, and was the attack did they get the information that they wanted, or were they stopped? And then you basically have some information about how, what exactly happened, and you have opportunities in each one of these phases for modeling whether or not, if one particular attack technique was successful, then did the person, or did the attacker try again, that sort of thing. So these are examples of a KPEC attack. KPEC is MITRE. MITRE's the corporation that basically publishes this information. It's a very large database describing a very large number of different attacks. So this is cross-site scripting. We also have modeled what do you call it, a SQL injection attack. So these are the, oh, I skipped one. Okay. So these are the various phases. Usually what happens is it will start, you'll start here. This is the initial marking. This transition is then active, and then it's the only transition that's active, so it fires next. This place is then marked. This is basically saying, okay, I'm attacking. And then you basically have 4 different techniques that you can do in order to see whether or not, what happened. Well, 3 techniques that you do, and then 1 fail technique, I think. So at every stage there's something happened and I decided to stop attacking option. So that's what this is. So there's 3 techniques here, and then there are various success, success but detected, and then fail type options here. So this transition right here is a succeeded thing. So basically, if this fires, then this gets marked and this gets marked, and when this is marked, this basically says, okay, now I can proceed to the next phase. So you see how he's connected here and also here. These slides really bring this thing up. Can I see this in better? So this is the same attack, or this is the same net. It's a little bit easier to see, but it's still kind of difficult. You generally see how this is laid out though. So in the UAH group, research group that I'm a part of, there are actually 5 projects that are all independent, but working together. One was basically saying, hey, let's look at the programmatic, or the XML data that KPEC has, and let's see how easy it is to take this information and generate Petri nets with it. And so that they basically proved that, and they were able to produce some see this. This is actually an example of a Petri net that was programmatically generated from a KPEC attack. And this is not. So then another one is a reinforcement learning study where they're basically taking an attack and adding the idea of, so you have attackers and defenders. Well, what you can model attacks with that, but oftentimes in the real world, regular users can also theoretically trip systems that are designed to detect an attack, and so you could theoretically achieve perfect security by unplugging the server, but then then it's not very useful anymore. So how do you go about actually modeling valid use of the system as well as detecting spurious use of the system? And so this is one of our researchers is looking at setting, like figuring out how to model that kind of how do I like, what does it look like when a regular user is using this? I'm not going to be able to dial all of my security up to 11 because that would kick out real users. So how do we model that using this formalization? So then another one of our researchers is looking at taking the individual attack techniques that are described in the KPEC database and basically breaking them out and then building a constructed or a composed attack. So basically saying this particular type of attack might be useful in more than one attack type, and so how would we describe hybrid attacks within, like, from the KPEG library? And so they're looking at like the outputs of, like, what are the results of certain attacks versus like, if I go dumpster diving, I'm not necessarily going to get the same information that I would get if I do a spidering of a website, that sort of thing. And so I can't just say, okay, any attack is going that succeeds is going, or any attack technique that succeeds is going to allow me to transition to the next phase, because like for a particular attack type, it might not. So we actually have to look at the products of various techniques, and some of them you have to. There are prerequisites. There are data types, or there's information that you need in order to start a particular technique. I need to know. Where a company hides its trash, that sort of thing.
Well, I guess a Bayesian spam filter would kind of be an example of this, where you're providing feedback to it on what got flagged properly and what didn't.
So that would be more. I think that would probably be more what the first research thing is kind of talking about. You definitely want to, you can't dump everything into spam. Like, you have to be able to recognize real, real email traffic. So, and then the fourth research topic is actually, it's verification and validation. So verification is, did I build the thing right? And validation is, did I build the right thing? That's a systems engineering verbiage to basically say, did I meet the requirements and did I write the right requirements? So that's like, verifying that a model is right is basically saying, I took the data that I had and I wrote a model that was true to that data. And then validating is saying the data that I had is actually a real description of the reality that I'm trying to model. So that's kind of the difference between those things. And verifying is easier than validating. So I can basically say, oh, look, this net matches the outputs of this KPEG attack, and so there's a one-to-one conversion between the two. So that is a good verification. That's a very good verification that what I'm producing is true to my inputs. Validating an attack basically means was this attack pattern a real attack pattern? Like, so now you're looking at, okay, how do you prove that an attack pattern like is a thing that actually happened? Because that gets a lot harder. Companies most times don't really want to announce that, hey, they got attacked and it was successfully defended against, because they don't want to give attackers information about how they did it. Likewise, a lot of companies don't really want to talk about successful attacks to researchers, because now it's going to make them look bad to their customers and stuff. Say again?
Investors?
Yeah. So validation of these attack models is a lot harder than verification. In the past, what we've done is we've gone to cybersecurity experts and shown them an attack pattern and said, "Hey, does this look like reality to you?" And then they'll look at it and go, "Yeah, that looks like reality." We actually did that for a couple of attacks, and they threw out one. Like they basically were like, "Yeah, I don't know. This is too. There's too much variance between this and actual attacks that I have seen for this to be a useful model of this type of attack." And so they tossed it out. Yes.
Oh, is the sort of end goal to feed this to like an IDS or something? Where does the math meet the? What's is there some kind of product in development or?
So this is pure research, but the idea behind this is we want to be able to prove this technique as a useful technique for feeding trade studies and showing different kind of reactions, like different defense patterns are more or less useful, in particular attack types.
So by labeling attacks a certain standard, defending the responses would be then be.
Mm-hmm. Yeah. So one of the things that we did, and so the last one is one of the ones that I've been looking at, or that I've been doing, is basically using reinforcement learning I've mentioned it a couple of times because that's kind of what I do. I'm picking up another another doctoral student's research. He defended a dissertation based on this, and I'm extending his research to in the reinforcement learning realm, and basically applying his technique to the technique that so basically what he did was he took CAPEC attacks and then hand built these nets. So what I'm doing is I'm taking the generated the auto-generated nets, and I'm applying that to it and proving that this also is a thing that you can do. It's the difference there is that the attacks have changed between enough between when what he was doing his research and when I'm doing my research, that there's that comparing the outputs are going to be a challenge too. So for me, the verification is going to be an interesting problem to solve. So, yep.
So I'm thinking about maybe modeling PhreakNIC, so you have your model, say, CIS container level 1 or CIS container level 3. In terms of CIS has some AWS containers that you can develop software on, you can install software on, and some of these are hardened more than others.
Mm-hmm.
And you can do some things like take an attack, model it, and then throw it at one and see what comes out of it. Does it match? And since you're looking at validating, does your model match what that system can do, or does it not? Is there some way that you can break the application sitting on that system with the net? And if you can, well then can you do that in a deterministic way? Do you know where the edges might be for that?
So this is so Petri nets are they're not really a control structure. They're more of a way of describing a process. So basically, there's no way to other than by changing the transition rates, like between for the transitions, to say, okay, I have gotten this particular type of marking, so now I am going to do this particular activity, and I'm going to get this this result. They're more there still is a level of randomness involved. So what you could do is you could train agents on a Petri net, and then take that take the strategies that are developed from that, and then map that into some some other simulation, and then you could then play war games with those strategies. But as far as map like using a Petri net as some kind of control structure on a in some ecosystem, that's some of these. So a lot of times when we look at these graphs, they look like other graphs, like computers talking to each other, or layers. That's not what's going on here. These are states that are basically moving back and forth, like basically that. So it's kind of it's a lot more abstract than I'm sending information from one VM to another VM, that sort of thing. Let's see. Any questions? Yeah.
Would validating comprise something where you make sure that every state that's represented in the graph is visited?
So what we do, and actually the one of the tools that we use for simulating Petri nets is a tool called Pipe, and that's what I have up here right now. And one of the analysis tools that Pipe provides is a way of taking a Petri net and then running it, a million times, and showing, yes, these are the various configurations, and this is the likelihood that you're going to see a particular kind of configuration of the net, and so then you can what it'll do is it'll actually give you it'll give you information about, let's see, it'll okay. So basically what this does, or what this is it's this shows all of the transitions and the likelihood, or that they're going to fire, and basically it's showing the arcs, and it's mapping that back to how the arcs are connecting around. So that's this. As you saw, it's pretty fast, but it's there's various analysis tools for looking at a Petri net and like looking at the global space, the marking space of a Petri net. Now, when you start looking at these gigantic CAPEC nets, pipe has been defeated by these very large nets. What we wind up doing with these things, guys is we break them up into their various phases, and we run the analysis over the phases, and that gives us the information that we want. But yeah, these are very like anytime you see a transition feed backwards, well, now you've multiplied the complexity by a lot. So, any other questions? Yeah.
You said these are auto-generated?
So one of our grad students, he successfully defended his dissertation on this. Built a tool that took the XML and generated CAPEC or generated Petri nets from the CAPEC attack description, the XML files.
So those are standard descriptions in the CAPEC database?
Yes.
Okay. I was curious if there was some kind of machine learning aspect involved.
He had to do quite a lot of mapping to like keeping track of tag information, basically making sure that the various terminology matched up right, because most of the CAPEC attacks are in English. Like they're basically a natural language description of the attack that has been basically broken out into like a format, and then he took that format and then further used that to build these attacks, these nets. So, you got a question?
Oh, it was the same thing as how they're auto-generated.
Yeah. Okay.
We have a question. Is CAPEC a publicly accessible database?
Absolutely, yes. Yeah, if you Google MITRE CAPEC, CAPEC, it's common attack pattern enumeration classification. I think I actually have that in the slides. Yeah, common attack pattern enumeration and classification. Yep.
Can you enlarge that?
I probably could have put this in display mode. Wouldn't that have been nice?
That's an maximum.
So if there are no other questions, I'm going to end this.